Okay, so I'm still not completely verbal, I'm not feeling bad, but my voice doesn't work very well, so I apologize. So there are two things I wanted to do this morning, well, three. So one thing is I'd like to review the stochastic programming idea again, just to go through it. And as part of that, I thought it'd be useful to talk about this Epstein-Zinn preferences and the representation of that in the sort of a GAM style format, which is these are typically used in recursive framework, but it turns out that they work fine intertemporally. So I've developed a little pilot model that compares that functional form. And in the process, I thought it'd be useful to go back through the stochastic programming, just the basic idea, just to make sure that that's clear, because it takes a little while to get your mind around it. And then the next thing I thought I would do would be to go through this paper called Local Warming by Robert Vanderby. He's a computer science guy from Princeton. And it's just a little estimation experiment or estimation exercise trying to uncover warming at a local level based on temperature. It does a little regression. Again, I have the GAMS code that goes along with the paper. I did that as an exercise for my class. And what's useful here is that it shows how to do a bootstrapping exercise. So where you estimate the model and go back and generate a sample set to identify. And I thought, again, just the GAMS programming aspect of that would be useful. So that's what I basically had in mind today. So the first thing is just to remind ourselves about these boards. These boards are rather problematic. What's that? Yeah, that's the worst. I'll use this over here. So, just to remind ourselves of how we do this. Let's say we have a tree that looks like I think we may be using regular markers on the whiteboard, which is bad. So, in this framework, we have a tree that we're managing. And so if we're going to write down if we're going to keep track of, so this is going to be state variables. So there's a state variable evolution equation you write down for a stochastic model. Capital stock evolves according to depreciated capital. The capital in state S in period t plus 1 is equal to depreciated capital from the previous period plus investment. When we write down that sort of equation using the scenario tools, we'll typically write the equation as K stock of n of t comma s. So if we think about what that does is that immediately we write down n. N will be the set of time periods and states for which we keep explicit accounting in the model. So we're only going to, here we've labeled each of the nodes with a scenario, and the scenario will correspond. So this guy would be labeled as scenario 1, but it also represents scenario 2 is also represented by that node. We could label this one as scenario 3, but it's going to represent scenario 4 as well. So in the model, we only keep a variable that corresponds to S1 in T2, and it's also going to represent S2 at the same time. And up here, for example, if we label this one as S1, this also represents S2, S3, and S4. So the notational structure for keeping track of the tree, the way it normally, so first of all, we keep track of n of t comma s, and in this case, n of t comma s would be, for t1, it's going to have s1. For t2, it's got s1 and s3. And for t3, it has s1 to s4. That's just indicating which scenario time pairs we're keeping track of together. So we write down the k-stalk condition. We say we only want to keep track of this accounting for the items that are in the tree. And we'll say then k of t comma s is equal to lambda times k of, and the notation you'll see here is going to be ts of t comma s plus I of ts of t comma s. So in the DICE model 2013 with stochastic programming, I use a macro to indicate which scenario really in time period t where scenario s actually sitting. That will point back. So if you're looking here, you're saying how much capital do we have in scenario 2, time period 3. This says if we look back to period 2, that it's going to tell us that it's actually scenario 1 is where the parent is. So this notation makes it, this macro hides the pointer back to what the previous scenario is. And if you haven't, so this is just a means of writing down the model so that it looks, the key thing is that you control, on the equation, you control the variables that are being controlled, only those time periods and states which are going to be modeled explicitly. And then on the right-hand side, when you're pointing back to the previous period, you don't know whether that scenario exists or not. So you use this macro. And what's the macro look like? The macro TS is a macro that will simply, the TS macro is simply just for appearance sake. It's going to be, you'll see it's going to be a macro above the thing. TS of t comma s is simply going to be t comma s plus o of s comma of t comma s. And this o points to what, it sort of indicates which scenario represents that point. Okay, so that's the process. So that's just a bit, just to review. So the key thing is that we want to manage the tree by identifying what scenarios have been identified at what points, at what time periods. And we do that through this offset pointer that indicates at a given point in time for a given scenario, it points to what scenario represents it. And that makes it possible then to write down your stock accumulation equations with a macro to point to which scenario in the previous period. Notice that if you're writing down an equation that corresponds to what's happening in one point in time, only in one point in time, then you don't need to use the pointer because you're already restricted to a scenario that actually exists. You're just doing the equation for that one set. So it's only for these ones that involve stuff across time that it's really important. Any questions? Yeah.
Yes. So if I understand it correctly, that pointer thing is only necessary because we want to be efficient and not have redundant. So if we were programming a little less efficient, we could just point directly there at the parent node, and we would have.
Then you have to add these constraints, and the constraints have just as much logic in them as this does.
You would have a constraint that the node S31, 32 would have done the same as S.
You have to add a constraint saying that x of S2 in T2 is equal to x of T2 and S. Writing the constraint is hard as writing the thing down. So I'm just pointing this out. Okay. So it's just to be clear. Yeah.
So if I'm in state 4 at time 3, and I want to refer back to time 2, would my offset pointer would just be -1?
That's right. O would be -1 at that point. So O will just point back. And it's just a cheap way of managing the tree.
Yeah, but if I'm in state 3 and time 3, my offset pointer would be 0.
That's right. So that's the way you can identify how do we assign set n. We say n of t comma s is equal to yes, such that O of t comma s is equal to 0. So the set of nodes that we need to keep track of are those for which they've been revealed. So, so before I go forward, there's one thing I want to also point to. I want to point you all to a paper that's on the web. The Betty Crocker paper. So this is Richard Howitt has a nice paper that follows up pretty much very closely on what we did here. If you decide that you really would rather use dynamic programming, this is a paper that shows you how to do dynamic programming. If you don't want to write out the whole tree and you want to do the thing recursively, this is a paper about how to do that with GAMS programs that shows how to do it. So it's just Richard Howitt has so the tools that we're using, you can do things iteratively in that setting. So it's if you just say, do a search for Richard Howitt, Betty Crocker, then you get it. So now, let's talk about preferences or sort of risk attitude. Because I've learned a lot this week, I have to say. I like this work. This has been a really good week for me. I've got two really great ideas from the week. So one is this idea about Epstein-Zen. I now understand exactly how this works, and it's good. And the other is this idea about Bayesian learning on temperature change is a good idea too. So it's been very interesting. So let's talk about the stochastic structure, because I think in your paper yesterday, I was noticing there are three ways that we've seen this week for representing this risk, expected utility formulation. And one, so if we have C of S comma T is consumption by state and time period. So one way of doing this is to say and this is down through a tree. So one way of saying this is you could say the utility that we in state S, if state S appears, is going to be the sum over T of delta to T times U of C sub ST. So delta is the discount factor for time. Yeah.
I apologize. Can we go back to the last slide?
Okay.
So if I'm in time period 2, right, we start stopping at 1, yeah. Do we know whether we are at node S1 or S3? Is it in principle possible to know whether we are at node S1?
You don't, they're always going to be the same. We're imposing that they must be the same.
S1 or S3?
What's that?
Do I, in time period 2, do I know anything about which branch I am?
Yeah, you'll know. In the model, you'll know it's either S1 or S3.
Okay, I know what the realization of the first period was.
What we're going to do is set up the optimization problem for how agents optimize, given information that they have both about where they are and what the probabilities are of the outcomes in the next period, and then we'll solve for the maximum.
I'm just confused about that. The point we can use for both the first period and the second period.
Yeah.
I mean, they ask one.
Call them with different names. Maybe let's call them node 1, 1, node 2, 1, 2, 2, node 3, 1, 3, 2, 3, 3, 3, 4.
So the other way to do it, and this is described in my paper, the student's paper, in his paper, you can put a node system on it, and then you have to keep track of what node corresponds to what scenarios. So there's some people like doing it that way. And Yves decided to hedge his bets, and he has code for doing it both ways, right? So this is going to be so there's going to be a parameter here, and normally you would write this if we have CIES, that's constant intertemporal elasticity of substitution. It's going to be delta to T times C sub T to the 1 minus theta all to 1 over 1 minus theta. So this is what, theta is what Nordhaus would refer to as the marginal elasticity of intertemporal substitution. And then expected utility then would be equal to the sum over S of P sub S, the probability of state S, times U sub S to the 1 minus R. So that's R is the coefficient of relative risk aversion. So that's one way of doing it. This is one way. I'm going to go through 3 ways. Yeah, so the other way to do it was in the paper yesterday. The other way to do it was to say the utility in state T is going to be the sum over S of PS times C sub T sub S sub TS to the 1 minus theta, all to 1 over 1 minus theta. Should be TS. Is it ST or TS? TS. And then you'd have EU then would be equal to the sum over T of delta to T times U sub T to the 1 minus R. I have, there's no rule. In consumer theory, preferences are only known to within a monotonic transformations don't matter. So in principle, I don't have to put the 1 over, I could divide by 1 minus R, or I could put it in the denominator, I could put it in the exponent. In most intertemporal models, it's conventional to put it in the denominator to divide through. But I don't like that because I like to have money metric utility. I like to know that a 1% change in the utility index corresponds to a 1% change in expected income. It's just a matter of convenience. It's helpful to know. So those are 2 ways we've seen. This is the method that I used in the DICE 2013 model, and this is the method that was used in the paper yesterday. I forget your name actually. Delph had a very nice paper. So his framework is like this. The problem with both these approaches, they do distinguish between intertemporal elasticity, and they do distinguish between that and attitude toward risk. So there's not. Notice that if you make R equal to theta, then they combine into one. Then the attitude toward risk and time is the same, and it all sort of folds together. But if R and theta are different, then you have different attitudes. But then we learned the main problem with these is that they're not time consistent. So if you solve the model into the tree, you initialize at a given point in the tree and resolve, you won't reproduce the same results.
I have 2 completely different properties. So the first one does not satisfy ex-ante efficiency. That is to say, you can find another stream that increases the expected welfare of the people, whereas the expected is the sum of the, as a one-time below, which is the aggregation of the expected utility. Whereas the first one satisfies state-wise independence, which is also a nice property that says, suppose that in each possible scenario you can be better off. Then the idea is that this allocation is better than the previous one, and the second does not satisfy this property, and the first does.
Okay.
So there is a trade-off, and it's a difficult choice.
And then finally we have this, the Epstein-Zinn formulation is one where you're going to have U of S comma T is going to be equal to a term that says there's going to be some weighting term, say beta, times C sub S T to the 1 minus theta. I probably got this wrong. 1 minus beta times V sub S T to the 1 minus theta all over 1 minus theta. So V sub S T then is the expected utility, which is going to be equal to the expectation over the U of S in T plus 1. So it's going to be S prime in T plus 1. So there's going to be a utility function here that's going to be 1 minus R to the 1 over 1 minus R. So in the recursive, the Epstein-Zinn formulation, your utility depends on current consumption and the certainty equivalent of the future welfare. And so the interesting thing is, okay, can we do these things? Normally you think, well, if we're going to use that sort of formulation, normally you'd think, well, we have to do something dynamic programming like. So if we look at the, so here's the model for today. It's called example. So I'll post this for today's lecture. This is a lifetime endowment model with Epstein's in preferences, and compares it, what comes out of that model with what comes out of the previous two models. It's very simple. So this is a model with finite horizon. So it's a life cycle decision model, and it has incomplete markets. So individuals can't insure against all possible contingencies. So there's going to be so R is going to be the set of realizations. So for the time being, let's not worry about SGen. Just SGen is the thing will automatically, it's going to say the realizations in any period will be low, medium, and high. These are just normalizations for which one how I want to manage the naming of the scenarios. And then I'm going to have the time to be from 0 to 8. So we have 8 periods. And then I'm saying, well, what's the first period? Is TF is the first period, TL is the last period. And then we have 2 parameters. Gamma is going to be the coefficient of relative risk aversion, and phi will be the elasticity of intertemporal substitution. And then we write down to describe the transition in the tree is going to talk about the probability of transition will be between realizations. So in this model then, every node in the tree is a particular realization, and then there's this Markov transition matrix describes the probability of moving from one realization to the other. Okay, so that part is that's different than what we did in the dice model. So this is one that will be, and as we see it, we have, you basically, once you get in the low state, you'd have a tendency to stay there for longer. We could compute what the steady state probabilities are from the matrix, but I don't do that here. So the previous, the call to the other one, I probably should have done this one above. To be clearer, it should have been better. So we're going to keep track of O, which will be the offset pointers we use for managing the tree. And then we also have a thing that says SR indicates for a given period T and a given state S, what's the realization in that period. And then we have, once we've got that, then we can set up another set that says when we're in state scenario S is represented in period T by scenario SS. So that's just another way of keeping track of which scenarios are sitting in a given node. And then here's the macro that will point to where these guys go. So if we got this, let's just look at what the model looks like. So we have, before we go through all the logic of generating it, let's just see what the model looks like. I'm going to be better off if we get these guys. So the first thing is we're going to say the variables will be, so we've got A is the asset position at a given time period in a given state of the world. V will be the continuation, the expected utility in the next scenario, in the subsequent period. So U is the expected utility if you're in the state, and that's exactly this expression here. It says, I got beta and 1 minus beta wrong, so it's 1 minus beta times C divided by C graph to the row, plus beta times V to the row. So that's an ordinary CS elasticity, and has this parameter rho that describes the elasticity of intertemporal substitution. And then V of T comma as, so it's got this sort of messy looking thing, but it's not, it says that ST is a set that says if we're sitting in scenario in time period T in scenario S where we have realization R, we then in the subsequent period we might moving to scenario SS in period T plus 1 with realization RR. So that's just keeping track of what's happening in the next period. What are the set of scenarios we have below? So if it's like if we're sitting in if you're sitting in S comma, you're sitting in S comma T, or T comma S. This is T comma S. You're going to have one of the scenarios will be T comma S, because once the scenario evolves, but there's T comma S prime and T comma S double prime. So we have to keep track of what all the subsequent nodes are, because we're going to be thinking about what the probabilities are moving from this state to the subsequent states.
What is knowledge in the objective function? What is your summing order?
Okay, that's going to be the node objective, and that's just a way. What I did is I set up the model because I wanted to verify that I have time consistency. So I first will set n obj to be time period 1, the first scenario, and solve the thing all together. And then I want to go fix the asset positions and go through and verify that I have time consistency, just to show that. That was the idea. So it's, the other way to say it is you could say, you could simply say, and to make it simpler, it'd probably be better to just say TS of TF comma S. So that says in the first period, whatever scenario is in the first period, just maximize from the top down. So V of T comma S says what is the expected utility that I'm going to have in the next period based on the probability of the transition from T to the next period. That's this transition matrix. It says that I'm currently having realization R, and I could have another realization RR in the next period. And so Ptran is this transformation elasticity. And then U of T plus 1 comma SS tells me what's the utility I'm going to realize in the next period. So it's just simply saying. And so gamma then is the elasticity is the coefficient of relative risk aversion that has to do with how you aggregate expected utility across realizations in the next period. The previous thing is just simply saying what's my asset position. If I have a reference price path, PREF, that's simply keeping track of what the future value assets are in period T plus 1 as a function of what the assets are in period T. It's an endowment economy, so E of TS comma T is keeping track of what the endowments are, and C is simply the level of consumption. So the assets in period T plus 1 is the assets in the previous period plus the endowment minus the consumption. And then finally, the first constraint called budget says that we get to the last period in the model, the assets plus the endowment equals consumption. So it's simply saying we have incomplete markets. There's no opportunity to hedge against risk. If you happen to have a bad outcome, then you have to basically anticipate that consumption has to come down to match it. So that's a simultaneous representation of the recursive preferences in that setting. So now to compare it, I was curious about how does this compare with what we have. Notice here, and in terms of setting up the model, you have to set up the model by initializing. That's just to help things. You have to say, well, the asset position in the first period is going to be equal to 0. And then this one's going to say the asset level is you just initialize. And then these lower bounds is just to help the solver. There's this problem that in GAMS, if you're using the optimization tools with nonlinear functions, you're responsible for keeping the variables bounded away from points where the functions can't be evaluated. So that's simply saying, that's putting bounds on to prevent bad function calls. And so that gives us the whole thing. Initially, I solve it with no assets, so there's no opportunity for borrowing or lending. And then I remove those bounds and solve it again with borrowing and lending. So the borrowing and lending provides an opportunity for borrowing against the bank. And then once I've got that solution, I save the value I save for the reference case. In the EZ model, what's the value of A, U, V, and C? I store those guys. Now let's just go down and see. So the next model we have is one that has intertemporal utility for state S, which simply says, again, I'm going to say, and again, this NS and NT I just put in because I wanted to be able to identify, I was trying to set up the model to show that we don't have time consistency in this model. So that was just for keeping track. I wanted to be able to suppress part of the tree to solve it separately. But this says That's the intertemporal utility of consumption along that scenario. And that's just simply, again, I'm using, notice that to get the consumption in state, for state S, what's the consumption level for state S in period T? I use the macro to point to what scenario pair represents that. And then this is the rho elasticity of the primal elasticity with respect to time. And then the expected utility in time. Again, here I'm aggregating across scenarios, and then I have this elasticity there. So it's those are the two different formulations that we went through. And if we have SWDEF is where we're looking across scenarios of what the intertemporal utility is for scenario S, or if we're looking at IWDEF, then W is equal to this is the substitution across time of the expected utility at each point in time. So those are two different formulations. And again, a lot of this, for the purpose of sort of getting your model clear to understand what's going on, you always begin from a value that you know. And so in this case, I've noticed that I've calibrated the models in the sense that I put in the CREF, which is the reference consumption path. So if the prices move with the interest rate, then consumption moves with CREF, and their optimal choice about how much they want to borrow will be 0. So I set up the model so that and the preferences are set up so that if interest rates follow the rate at which they can borrow, their endowments grow with potential along the same path, then there's no demand for investment. So that's what I'm doing here is I'm simply doing a solution, and then I say, okay, I know at that solution, I know where I am. I know that W should be equal to 1 at that point. I've just scaled it so the welfare is equal to 1. If it's not equal to 1, I know I have a mistake in the model. So at this point, I set up the model, and then I pull the plug. If this model does not calibrate to 1, then I know I don't have something right. So I've just set up the model, so I first solve, and I get back exactly what the baseline path is. And then I store the results at that point for both the reference cases. And then after having calibrated all 3 models and verified that they all replicate, then we go in and say, okay, let's randomize the endowments. So we just randomize the endowments along this path. So this is just simply saying, we have this growth rate in the transition. I'm saying if in T plus 1S there's realization R, then the endowment in T plus 1S is going to be the growth rate in the corresponding realization times the endowment in the previous set. So this is the way I set up endowments over the whole tree of the model that reflect what the realization outcomes are in those points. And that simply says I do a display just so I can see how much randomization I have. And then at that point, then I can solve my Epstein-Zinn model with NLP maximizing W. And then here I want to be able to look at the results, but there's a ton of scenarios. I have 8 periods, so this has got like 88, or that's a big number of scenarios. So what I do is I just get the scenarios which are, I look at the case in which the realization was M the whole way through, or if the realization was L the whole way through, or the realization was H all the way through. So I get a sense about what the range are of values that come out. It's not telling me how much variation I have inside. And then I just record that solution. So here I'm just, the solution was being recorded for the purpose of demonstrating the time consistency. So that's really not relevant. I basically harvest the results, and in my pivot table, I want to be able to identify not by the scenario number, but by what the realization is that corresponds to that path. So I set up this mapping to map from which scenarios correspond to a single realization at all points. So this is simply saying, look for a pair of scenarios, the scenario in the tree where you have either L or M or H all the way through time, and then those are the ones I want to save. So I take the values from that scenario and put it in with that label R. So this is basically getting results, and I do the same thing then with the other 2 models, and then I dump it out into a spreadsheet. Yeah.
Question about market completeness. So suppose that, do you think that time inconsistency, if the market is complete, that you can eliminate all your systematic risk? Suppose that you would have another player and that you can perfectly eliminate everything,
So in this model, if you give them a single budget constraint, then they basically just have flat consumption the whole way through, because the states of world basically balance out, and so on average your income is equal to 1, and they'll completely hedge everything. So in this model, doesn't matter. So time consistency matters when you have incomplete markets. That's the main thing, where you can't hedge against everything. Yeah.
And by finding these intervals for the functions that you mentioned, you exclude corner solutions, I guess.
So the corner solutions would be, in this case, we have one consumption good. They can consume out of their assets, so we don't have a market. Okay, so I have excluded the fact that they might want to consume more than there's available in the market at that time.
Does counts like a reward when you are close to such an extreme point?
So in this case, it's as though it's the endowment. Essentially, it's as though you're actually physical. The asset is actually a physical asset. So that's an interesting question, would be to put in a constraint where you have an upper bound on how much you consume in a given period. But then you'd have to be clear about what is the opportunity for stocking from one period to the next. Yeah. So that's an interesting question. Clearly this model, I was just trying to get at the essence of how do we represent these other preferences. I was trying to focus on that, but extending this to have multiple agents or to have different types of time is interesting. But the thing so I just wanted to, the key thing here though is these numerical values, and in the two cases, you're going to find that, so here so this is the case, this guy, let's see if I got, it's going to be over here, analyze, what's going on? Analyze. So if I say here, so this is looking at item here, I'm looking at A. So this is the asset choices in the different scenarios, so that this left one is where you have a realization of the high outcome in every case. So if you have an outcome, so you're hedging against the possibility of a low outcome. So in that hedging, if it turns out that every roll of the die tells you a high outcome, you develop a positive asset position over time. And this shows what happens. And the key insight is that the elasticities, there's some difference between these, but not enormous in this particular case. Okay, basically, there's a small difference. So if you always roll the median outcome is always realized, then basically the asset position remains close to 0. Whereas if you have the high outcome in every case, then you tend to build up assets. If you have a low outcome, you tend to run a deficit. You could, in this model, put in an upper bound on how much, or you could put in the borrowing cost to be higher or lower depending on your position. So there's a variety of ways you could extend it, but mainly in terms of the preferences, it doesn't seem to matter a lot. If we look at consumption changes, those are also very close. So the consumption, in the case where the agent realizes a high rate of consumption in every time period, then the consumption jumps up a lot. If it's flat, then it basically doesn't change very much from the reference case. And if it's low, then it tends to go lower and lower over time. So the main objective here was just to go through one more model. Yesterday we hadn't done a model that had this Markovian transition. And so in this setting, the stuff that was tricky in the EZ model that I hadn't seen before was simply the evaluation of V is what's tricky here. Because if you're sitting in T in state S, you have to write down what's the expected utility if you're sitting at that point, and that involves describing what's your realization you currently have, what are the states and realizations you could experience next period, and then get this transition. So setting up this array was the main programming trick here, was to get this guy. And you can see the logic for how that's established. But once you have that identified, then it's, I think, all pretty clear. Okay. So I realize this is strictly methodological, but just for sharing you, for understanding how the programming framework works, I think it's helpful.
Basically, the point that you're making is that when you do work with an objective function where
You have to, it's just, you keep through the accounting to figure out what the transitions are from each point. That's the main trick. But my conclusion here is that there's nothing, we could do this sort of preferences in merge without any trouble. So the finding that's exciting for me is that this not, you can do the Epstein's in without doing recursive solution techniques. You could just drop this into the models that we currently have. Yeah.
So your B, does it capture the uncertainty one period ahead, but does it capture the uncertainty all periods?
It's defined over U in the subsequent period, which captures everything subsequent below that.
U is capturing everything.
Yeah,
Capital U.
because the U of T+1, that U captures everything that's happening out to the horizon. So that's the reason you get the whole thing there.
Is you're summing over this, so you're summing over this well-defined set of nodes that come out of those.
No, but the point, his question is, the point is that when you're in period T, and then you construct what the continuation utility index is, you just need to look at the utility indices in each of these steps. You don't need to go further down, because the U that you write down there, these U's in T+1, that utility captures the utility in that period and all subsequent periods. So that captures the entire train. So you don't need to write out in the tree everything that's down below. You just keep track of what's going on in the next period. Yeah.
So I'm really a bit confused because for me, actions is, so you're saying you're solving it non-recursively, but from what I know from theories, it's inherently a recursive concept. It can't be solved.
No, that's the reason I'm doing this is Sven's advisor, or Traeger told me it's impossible to solve, and I had this sense that it was possible. So that's the reason I'm excited this week. I said you should be able to solve this in one shot.
And I'm just wondering whether solving it non-recursively may be missing some crucial points from the theory. Because I don't know how you can solve it numerically without solving it recursively. If theory tells you you have to solve it recursively, that's the crucial thing about those references.
The point is that when you write it down, if you write it down simultaneously, then all the connections between the adjacent periods are captured here. So it's, I don't know.
So it is in a sense recursive.
Yeah.
In some sense.
The recursiveness is written in the fact that we relate U and T and S to the consumption in that period and the continuation, that captures the recursion right there.
The theory isn't violated.
I'm just not sure how you can capture the continuation value non-recursively. I'll have to look at your equation.
There's the probability of transformation. This is the expected utility in the next period. And that's going to capture, that's based on the U's, which are the continuation utilities out to.
And you say U captures the entire continuation, but when I look at the next period, U is
V plus the ones in the next period. So each time you go forward, you're getting the next, yeah.
But usually I need to find that V and find the continuation value.
I am finding it, but I just find it together with all the U's. You do the whole,
Usually find it recursively because when you look ahead, I'll have to look at it. This was fantastic.
yeah.
I guess the issue is the following. Suppose that you have to maximize utility at T+1 and utility at T, whatever is the node where you are at T+1. So if you maximize them together, you have two objects and you don't know which one is more important. You cannot just maximize the first one because then you might not maximize the second one. So the idea is that you maximize the second one and you move backwards. And for that you need that recursive form. But here you're saying that you do everything together.
We keep track of the whole tree at one time, and at the end of the day, the Epstein's in essentially maximizes the utility in the first period, anticipating what's going out.
So if you maximize utility in the first period, why do you have a sum in the welfare equation?
It's kind of messy. I could write it down. If you wanted to be more explicit, I could say, if you wanted to be explicit, that's just a way I can pull off what, without identifying the set, I could simply say this is U of T1, S1. Right, I could write it down. If I knew what those were, I could write it down explicitly and then it would be, but this is just a way of writing it down as the sum over t is just a way of identifying there's only going to be one scenario in the first period.
Okay.
So it's just a way, I don't have to know what the names of them are. It's a little bit, it's a way to pick off a single. It's picking off one element. So I don't know.
Yeah, I'm very confused. I mean, I don't know enough about the numerical stuff from theory. I just don't.
So it's going to be, yeah, I think the theory position would say, I'm going to maximize over C sub st and A sub st plus 1, U of C, A, and so you're basically saying, I want to choose to maximize current consumption and how many assets I leave to the next period. So, and my utility function has a particular normalization for how consumption affects it, and the asset return depends on what happens, how the asset affects utility in the subsequent period. And so you say that that's what the choices are in each period, and that, anyway, I'm not explaining very well. I'm pretty confident that it's right, but maybe. That's, I mean, the thing is, the V represents how much utility do I get in what's the expected utility if I'm sitting in time period T in state S? What's the expected utility that I realize in T plus 1 in any continuation states? I can look at all the continuation states. That's the expectation is the P-tran, so I'm taking that, times E of T, U of T plus 1 and SS represents the utility I will realize in the subsequent period, and that will be affected by the level of assets that I have, that I leave for the next period. Yeah.
I think this formulation might break down a multi-period framework. What she had on what Stanley had yesterday is really the two-period version. So her transformation and her definition of the certainty level that might not hold in the multi-period framework. But you said what really confused me about your presentation was that you said you checked for time consistency and you found time consistency in your solution.
Yeah, this one is something.
That's correct.
But your definition of time consistency is that you choose the state best alternative.
I fix the assets throughout the whole matrix, and I go to I pick any node in the matrix, fix the assets that I inherited, and I maximize down the residual tree.
So the first best alternative remains the same.
Yeah, that's right.
Time consistency in the literature is that the whole ranking should remain the same. Take any two class of choices, you prefer one to the other in whatever node. While your idea is more of selection consistency. So you choose, you optimize, you choose the path, you choose an alternative, and this choice would be the same that you would take at any later node. It's a weaker node. But
I don't understand that, but that's okay. Yeah. Okay, well anyway, I'll give you the files. You guys can see if this is useful or not. I don't know. The thing that's tricky here, the programming stuff that makes this messy, is the construction of this ST array is the thing that's tricky. You have to say, keep track of, at time period T, and where state S, realization R has come about, and there's another state SS with realization RR in the subsequent period. So that's the main programming trick, is constructing that data structure right there. Okay, maybe I'm wrong, but I'm interested. It's the purpose of the week was to interact, and this was good for me. I like it. You know. Okay, so and this also illustrates how to use Excel. So there's practical stuff here as well. So it's like. So final thing, so the paper is there. This is just conclude with a exercise. I find this, periodically, in Wisconsin now I'm finding I have to go give talks for different groups, and so I've given talks a couple times for Rotary clubs and stuff and in Wisconsin, you get these guys who basically don't believe in climate change. I mean, the Fox News guy we listened to in the movie last night, there's some place where you get that. And so I find that for these types of people, it's useful to actually show concretely, here and now, like forget about climate models, let's just look at the temperature. And Van der Bijl's paper is perfect for this because it says, is it real, is it anthropogenic? So Van der Bijl says, well, do we find that there's warming? And so he gives you a reference to where you can get data for local temperatures over a long period, 55 years of data. He gives you the script for going to get the data. You download it. So this is just looking at one place, McGuire Air Force Base. So there's the daily temperatures over time into one place. So the point is that there's just a huge amount of noise. Stuff's moving all over the place. And so the question is, how do we deal with that level of, variation? So the box plots give you the ranges, and it's kind of hard to sell. If you think about what the temperature, the 55 years, there's a huge variation. Now, if you overlay a couple of years, then you can identify that there's quite a bit of, the seasonality is consistent across regions, but there's still a lot of variation within the seasons. So it's the mean temperature by day of the year. So there's this annual sort of fluctuation. And so there's box plots, the same thing. So if we want to try to estimate, is there a signal in this data? People who are scientific, I'm much more persuaded by the ice core samples about what's gone on. It's much more plausible. A geologic time frame is more appropriate. But again, I don't know anything about the theory of persuasiveness, but with locals, you like to say, here's the data for your area. This is where you can get the numbers. And you show the thing and then see if we can identify from that the existence. So the challenge is to identify, can we identify variation? And the problem is, if you look at differences, you get an estimate, 2.89 Fahrenheit per century, but the standard deviation is 7.4. So if you do this naively, if you do the econometrics naively, you can't really find a reliable evidence. So if you look for statistical evidence of how this goes. So if you do the calculation without being careful, and so again, the same thing is that you can look at least absolute deviation, least squares. Now this is something that's one of, the paper has a lot about this. I'm not as convinced about, but notice that you can say minimize the sum over I of x sub I minus x bar squared, or you can minimize the sum over I of the median of I minus x bar. So this is sort of an L2 norm. This is an L1 norm, absolute differences. So Van der Bijl makes a big difference. The fact is, when there's a lot of noise and there are outliers, then his argument is the quadratic formulation tends to put too much weight on the outliers. So he argues in favor of this approach. And so just in terms of programming, we had a discussion over lunch at one day. Somebody was saying they didn't like the fact that GAMS doesn't give you the absolute value. It does. You just have to say minimize the sum over I of the deviation in I, sub the constraint that deviation I has to be greater than or equal to x sub I minus x bar, and the deviation also must be greater than x bar minus x. So these two are equivalent. So we do least absolute difference. You solve as a linear program, and you keep track, have an upper bound. That's the way you do a box norm in this framework. So So there's also variation. If you look at the data more carefully, you also find these 6-year sort of averages moving around a bit. And so there's evidence of a solar cycle in the data as well. So that basically, he's going to say, okay, well, let's do a model. The solar cycle turns out to be around 11 years. 10.7 is what's predicted. So then we write down a model where we say the temperature in day D is going to be an intercept plus a linear term that increases with the day, plus a seasonal cycle that operates over a year of 365.25 days, plus a term that oscillates over the solar cycle of 10.7 years, and then we have an error term. And so the x0 to x6 are the regression coefficients, and you can solve either least absolute difference or the sum of squares. You can work with whether or not, if you want to not believe the solar cycle is fixed, you can vary that, but that's not so important. So I just wanted to show you the paper you can read. I just wanted to show you what the model was, and then I wanted to show you one of the things that's neat here. So if we look at the model code, so this is the way this looks in GAMS. So you have parameters x0 through x5, and then you have the positive and negative deviations. You have the temperature in day D as a function of that, and you want to minimize the deviation. So the deviation is either going to be the projected temperature D, the average minus that, or the temperature, their projected temperature minus the average. And then you minimize these deviations. And the solving using a linear program. So that part of the process is pretty simple. Again, what's cool about this is it gives you links to where you can pull down data from different places. So for the purpose of, if you have to give a talk to people that are in Iowa, you can pull out the numbers that relate to that specific location. So then if you do this, you get a reference value, and that's going to be, it gives you the change. And from x0, you can see x1, the trends of, this is that many Fahrenheit per day, which is 3.6 Fahrenheit per century. So that's basically, and the thing that's neat about it is he's done this for lots of places around the world. There's remarkable consistency around places. So you do this estimate from lots of different places, you get very similar values. I mean, there's some places that are getting cooler, but on the whole, this basically agrees, and the variation across longitudes is consistent with what you get. Or is it latitude or longitude? I guess latitude varies according to is consistent with the prediction. And then the final thing is we're going to do this bootstrapping to get a confidence interval. And the bootstrapping simply involves you take the data as given, you run your estimate, you get your deviations epsilon sub I, and then from that you want to randomize the choice of those epsilons. In other words, you construct a synthetic data set where you just randomly reassign the variations. Yeah, I mean, now there's some evidence you have to ask, well, are these IID or how are these distributed? But basically, you can do this calculation, and then you can run a variation. So this ends up getting, you get a 95% confidence interval between 3 and 4.4, roughly. So if I look at the bootstrapping, so the model here, you have this model code is here. I'm sorry, model.gms. So the model code says, use Mosaic as the LP solver. In your case, you're going to have to use CONOP, so it runs for quite a while. CONOP takes some time with this data set. I have a program that reads the data. There's always this process about identifying missing data and knowing how many days have evolved. So there's some messing around with identifying the data. That's done in a separate program. Then it's going to include the model code, which will solve for the reference case. And then if it's set for bootstrapping, then it goes into the bootstrapping. So that's the basic control code that does it. And then if we go to bootstrap, the key trick here is to set up this mapping. Again, I apologize for focusing so much on plumbing, but that's oftentimes where the challenge is. We want to generate a set of bootstraps, say 30 bootstraps from BS0 to BS1. And so we say is, to do this, we set up a mapping that says in bootstrap BS, the deviation, the value for the temperature, the synthetic temperature in D will be determined by the deviation, the epsilon that we had in DD. So it's just a pointer identifying how you want to resort the data. And so we do that by, you do a loop here. This is a funny construct. I say loop such that the ordinality is equal to 1. So I know that D first is the first day in the data set. And then that permits me to do a random draw here by doing a random offset with a uniform that runs between minus 0.5 and the cardinality of D minus 0.5. So that does this is random selection of the bootstrap item with replacements. So we randomly pull that. And so that's the programming, that's the main trick here, is setting up that mapping. Because once you have the mapping, then I do a check to make sure that everything's been assigned. And then here I do a loop over the bootstrap. So I basically solve with the current value of assignments. I record if I'm in the first iteration, then I basically assign what the reference values are for the estimated model, and I also assign what the deviations are, the epsilons are. And then once I've done that, then I can do an average temperature I'm going to reconstruct after each solution. I go over my mapping and I say D is going to be defined by what the deviation is in DD. So that's using the model that was estimated from the raw data to construct what the synthetic data set is. And that basically then constructs a new average temperature in each time period, and then we go through the loop and go back. Then the next time we solve, we have the revised data set, and that gives you a way to collect the data, and that gives you a simple way. So the bootstrapping is a useful method for dealing with data sets where you want to generate one sense about the degree of precision that you have. And so that gives you a little bit of, just one more GAMS program that shows you how to handle data and move stuff in. I don't know how useful it is, but yeah, so I'm just about done. So my intent, it's been a good week. I've learned a lot. It's really been fun. There's stuff still to follow up, but I'm happy to interact with you folks by email over the next year or so. If anybody wants to come and visit Wisconsin, I'm happy to have you. Welcome to stop by, and it's been really great. So thank you much.